Welcome to the January 30th Zoom session. This is preparation for test one. As usual, it's pretty free form. I have Infinity up and ready to go. And if anybody has any questions to get us started, I'd be happy to look over any. So who would like to be the first brave person to ask a question?
Could we please go over either number 17 or number 31 on the practice test? Finding two unit vectors that are orthogonal.
Okay.
Um, on both of those, I got the first one right, but then I thought the second one would just be a scalar multiple of the first, but I don't think that was correct.
All right. 17.
Yes, please.
All right. I'm going to share my screen. So find two unit vectors that are orthogonal to these two vectors. Enter
Yes.
your answer so that the first non-zero coordinate of the first vector is positive. All right. So let me copy down the vectors and then I'll go to my overhead here. Now your numbers may vary, so keep that in mind.
Yes, sir. So I, specifically I got the unit vector correct for the first half of this, right?
Yeah,
So I did the cross product over the magnitude of the cross product.
right.
But then what I got wrong was the second part, finding that second unit vector that's also orthogonal. So I guess if we
Well, let's,
yeah,
let's
let's run through the whole thing. It's probably better that way.
yeah. So it's a good chance just to review cross products. I'll do the whole maneuver here. Just pop the numbers into place. Um, Set up your minors and cofactors. That's an I. Remember, the middle guy is going to be negated, so J. The minor of I would be -5, 0, -3, 3. The minor of J would be 5, 5, 0, 0, 3. The minor of K would be 5, -5, 0, -3. And so, and then we just perform 2 by 2 determinants. This will be -15, and that's just 0. So -15. This will be 15. Well, then that negative attaches. And then I guess we're at -15 again. How exciting. All right. Um,
Yeah. So um the first thing I did was I just pulled out 15 as a constant.
yeah.
So
Oh,
-15 is a constant. So I had a vector of 1, 1, and 1. And
yeah,
then
that would
I
work.
did yeah, and then I did it over the absolute and then I did over the square root of 3. Um right?
Yeah,
Because
so what? So one rad three, one rad three, one rad three. You know what? Oh, I think maybe I did you do the minus version also?
I didn't do the minus version. I did a version where I did it as 15 over negative oh, I forgot a sign, didn't I?
You
Because
may
would
have.
-15 over root 3 also have been acceptable?
Well, there's only two unit vectors, so these have to be unit vectors, and they want the first. So yeah, you're gonna, no matter even if you left them as 15s
Hmm.
and you did this, you would still get this. In other words, you would get 15, what you get 15 squared three times, whatever that is, 675 radical. You'd have 15, 15, 15, and then rad 675. But it would still be the same thing. The only other, the one that jumps out at me would be just take the alternate version, the one that points the other way.
Okay. And that's
Um,
because if I were to imagine that unit vector as a line in positive space, the negatives would be that same line continuing below that plane.
Yeah. So there's
Okay.
only two unit vectors. One points one way, the other points opposite. And any other version you come up with will just be equivalent to what you see here. In other words, they'll all reduce down to these two.
Okay.
So I guess the way the problem is coded, they wanted the first answer to have the first coordinate positive. Now, the way I'm looking at the questions, these numbers are randomly chosen. Now, I don't know why I got lucky and I got these are kind of trivial, but it's possible that somebody else might get some numbers such that the numbers are like positive minus positive, so their answer might slightly differ. Um, but these are the two that jump out at me. All of the other answers would be equivalent to these two. What was the other one you wanted looked at?
31. It's the same exact problem. It's just different
Oh
numbers.
yeah.
So that's
Okay.
I think having gone through 31, I mean gone through 17, that that answers the question. So once I find the first unit vector, then the other unit vector is just going to be the opposite signs.
Yeah.
Okay.
Okay. So is you okay with that one? I mean, does this answer both questions then?
May I interject, please?
Yeah, sure.
Yeah, so I mean, when you're looking at that problem, you got to think about what it's really asking. It's asking for a normal. So if you did like Ned said in the chat, if you do the cross product of A times B, you get a normal vector in a certain direction. And so it's asking for a normal direction in both directions. So if you do B times cross A, then that just points in the opposite direction. And
Right.
that's really what it's looking for.
Yeah. Yep, that's exactly correct.
Thank you, guys.
Yep, visually, any two vectors, as long as they're not parallel, can always be placed in a common plane. And then from that, you can generate a normal out of them by the cross product. All right. Anybody else have any questions on this one? Let me make a comment here. This is critical. When you do cross products, as you know, it's really easy to make arithmetic mistakes because you got a lot of numbers and negative signs to keep track. So it's important to check your answer by taking the dot product with both original vectors, one at a time, of course, and you should get zero. So if I dot, well, either one, with the original vectors, I will get zero. That's a way to check your work. It's a rare case where you can definitively check your answer and know 100% whether it's correct or not. If it's not correct, even if one number's off, it's not correct. So we're going to take a look at, I'll share the screen here. Give me a second. So let's take a look at this guy again. Yeah, we did this one the other night, and funny enough, I was curious about because 700 meters per second is quite fast. In fact, it's Mach 2 because we were getting answers like the downrange was 60 something kilometers, and I was thinking, wow, what are they shooting there? Okay, nevertheless, we can still do it as a math question. So we have initial speed 700 meters per second, and at an elevation of 30 degrees, and it's from ground level. So, all right, so I'll stop the share. It's important to kind of get a sense here. We're shooting something at 30 degrees relative to the ground, and we're ignoring spinning and we're ignoring air friction and all that fun stuff. It's gonna follow a parabolic arc. Okay, so essentially, um, all right, so let's set up. So you always start with acceleration. This is standard. And when we're dealing with meters and seconds, we'll deal with the negative 9.8. We integrate acceleration to get velocity. And what we're going to get is we're going to get a couple of constants out of that, where I'm going to call the x component, I'll call it v sub x. Now this will be negative 9.8 t, because t is the variable of integration, plus v sub y, where v naught vector, that's the components. Okay. And then what we're going to do, that's where this guy comes into play. That's where I can create a triangle. And I know that 700 meters per second is the hypotenuse. So this would be 700 cosine 30. This would be 700 sine 30. Turns out that sine 30 is just a half, so it just becomes 350. For cosine 30, it's not so convenient. So give me a second here. I get my calculator. When you're doing these problems, make sure your calculator's in degree mode. So 700 cos 30 is 606.217. I'll just round up to 22. Okay. So now I've got a velocity vector. This will be the x component 606.22. And then this will be negative 9.8 t plus 350. Then we integrate one more time to get displacement. This will be 606.22 t plus some initial x component. This will be negative 4.9 t squared plus 350 t plus some initial y component. And since this is being shot from ground level, it makes sense just to set this as the origin. Why not? So that means that these guys are both 0. We can ignore them. So I've got a vector for velocity, and then I've got a vector equation for, let me just rewrite it so those r sub stuff is not there. We've got a vector that describes position. And this is adequate to solve most, well, actually all questions that you're given, as long as you have enough information. So, all right. So does everybody see how I got those developed before I jump into the solutions? Any questions on that? All right. Well, let me know. I can always. So what do they want? They want to know the range, how far down it goes, and they want to know the max height, and they want to know the speed when it hits the ground. All right. So the range is going to be this distance here. And so I look at my information here, and it's this guy here is going to tell me the range. It's going to be the x component of displacement. But I don't know what t is. I don't know the time that it hits the ground. But I can use this component here, the y component. I can make the inference that when it hits the ground, the y component is 0. And so that allows us then to figure out what t would be. You just factor out now one of the answers is 0. Of course, that's the one that was shot. The other answer is whatever that worked out to be. So 350 divided by 4.9. Oops. 350 divided by 4.9. 71.428. And that's seconds. So this thing's in the air for quite some time. Then I can take this is the when. Then I can take that and plug it in up here to get the how far down range. So 606.22 times 71.428. Now I'm truncating these numbers, so the decimal places may differ slightly, but I get the range. So the horizontal distance is 43,301.08 meters. That's the answer. which I found was amusing. It's 43.30108 kilometers. It's quite a far distance. Yeah, so yeah, 700 meters per second is Mach 2. It's even a little faster than that. So not only is this thing shooting far distances, it's creating sonic booms. Does that make sense on that question? Again, I'll pause if you want to digest it a little bit.
No, watching you set up the vectors makes a lot more sense on this problem. My doing the math isn't hard to figure out once you have the vectors set up, but for whatever reason, my brain couldn't process that from going from the acceleration to velocity on this problem was just mind-boggling for some reason, but it makes a lot more sense after watching you draw the picture and discuss it.
Okay, well, then thank you. And one of the things I always recommend with these questions is just get the V and the R set up. Just go through the rigmarole to get them all set up. You don't know what you're going to need, but here you have the full tool. You have the full set of tools. You know, and I think I mentioned this the other night. I've seen, you know, I have physics textbooks where they have literally like 25 formulas that are essentially just variations of what you see here, but each of these formulas governs a specific situation. And unfortunately, that means you have to memorize 25 formulas and all the situations they apply to. And my brain doesn't have that kind of bandwidth. So I've always recommended to set these guys up, and then this is where you kind of have to read into it. You have to somehow make an inference as to when it hits the ground, something here is relevant. In this case, it's this part here. That means the height of the object is 0. Okay. In fact, the second question, we already have most of the math done anyway. The second question wanted to know the max height of the projectile. Well, we can a couple different ways. If this is a parabola, we can just figure out its height by taking the derivative and setting to 0, you know, getting the max. Well, it just so happens we already did that. That's that guy right there. So the max height occurs when the y component of velocity is temporarily 0. Of course, it's going up, 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 and then down, down, down. And for that moment, it's momentarily stationary. So the max height occurs when not negative 9.8 t plus 350 equals 0. So that means t is 350 over 9.8. So that's going to be, because this is a parabola, it's just going to be half of what you see here, the 71.428. Messed it up. Hold on. No, I did it right. 35.714 seconds. That's the when it reaches its max height. And so then to get the actual max height, you take the 35.714 and plug it into here. And that will give you how high it gets. And let me go ahead and do that. So it's negative 4.9, 35.714 squared plus 350 times 35.714 and 6250. That's meters. And again, that's a big number. That's 6.25 kilometers. You don't need to put the kilometers in. I'm just mentioning that because I find it amusing. And then the last question was, what's the max speed? Now you can almost, this is almost like if you see the symmetry here, it's actually what it was originally shot off at. But if you don't, you can just take the when it lands, 71.428, plug it into the velocity. You just plug it in right there. That'll give you a velocity vector. And then you take that value and you find its magnitude, and that'll give you the speed. And you should get the 700 because that was the original speed that it was shot off at. Now you may end up getting like 699.98 because you did some rounding, but it should be 700. I have some more problems on my webpage that, you know, because I could easily come up with about 50 different questions on projectile motion. Everything's slightly different. So take a look at some of those for also seeing how problems are phrased and how to break into them. But in every single case, you basically develop the velocity and the displacement vectors, and then you just use those to somehow break apart the question. All right.
And the t would be the time when ry equals 0, right? From what we used for the range.
Yeah. Yeah. Yeah, exactly. Exactly. We want the y component of displacement to be 0. That's how far away it lands. So when it lands, we don't know the horizontal distance, but we do know the vertical, and that would be 0. All right. Um, all right. Well, again, any other questions on this one?
I'm not sure that it'd come up in the exam, but the angle, it's come up in the homework problems where it's what is the angle when it hits the ground as well. And I remember it being reasonably easy to figure out, but for some reason, I just never remember what that is.
Well, if you get you can calculate actually right here, you find out when it hits the ground, and then you plug, no, actually, hold on. I'm sorry, you wanted to know the angle it hits the ground. Okay, let me think through that. I would do it. Uh,
In the questions that I've seen, it's like, and it typically is it's something shot from a cliff or it's something shot from a height. So your starting point, like it's a
right.
parabolic arch, but you're actually up by 100 meters type of thing. So then it
Yes.
asks at the end for what is the angle when it hits the ground.
You would take the arctangent. You would find the velocity when it hits the ground. Velocity will have the two components. So you'll have basically a right triangle. Basically, you'll have a situation that you figure out the velocity vector is coming in like that. And so your velocity vector will have two parts. I'll just call them Vx and Vy. So Vx would be this guy right here, and Vy would be this guy right here. And then so the angle of when it hits the ground would be the arctangent of it would be opposite over adjacent, Vy over Vx. So if you've got the velocity vector developed and you know when it hits the ground, then you can get the full vector, and then you can just come back up here. In fact, in this problem, we know that it hits the ground at this time, the 71.428. So if I can actually right here, if I plug it in, I'm going to do that. So 71.428, give me a second here. The second component I get is basically negative 350. And so that would be my y component. So if I do arctangent of negative 350 over 606.22, now remember I'm rounding. Sure enough, I get negative 29.9999. So basically 30 degrees. Because it's coming down like that, it's going to be a negative, but you can just strip off the negative. So
Thank you.
yeah, so once you've got once you've got the velocity vector when it hits the ground, then just use the arctangent to do the angle that it hits the ground. And make sure you're in degree mode. So this is one of those questions that whenever you do projectile motion, you're going to be in degree mode. Now, some of those work and torque questions will probably be degree mode, but in every other instance, especially like when you're doing like space curves and stuff like that, analytically, you want to be in radian mode. So just be careful with that. All right, so this is 41. A dense particle with a mass of 10 kilograms follows the path r of t. It's just sine 2t. Now, this is a case where you use radians if it comes up. Let's see. We want to find what's the force that acts on the mass at t equals 0. Well, I'll stop the share. Well, we're going to use that old famous formula, force equals mass times acceleration. And so what you need to do is take a couple of derivatives here. The first derivative will give us velocity. So this thing is basically moving along like a helix type path. You get 2 cos 2t, negative 2 sine, negative 5 sine 5t. This guy's going to be 9t to the 7 halves. Making sure I did that. No, that's not right. Is that right? Yeah, it is right. And then we got to do it one more time. What do we get here? Negative 4 sine 2t, negative 25 cos 5t. I do this one more time. That's going to be 63 over 2t to the 5 halves. And so we just plug in 0, which kind of is boring because it drops out 2 of the terms. At t equals 0, the acceleration at 0, well, that drops out the first and the third term. And we get negative just 25. It seems a little too easy. Okay. And so, give me a second here. I'm going to take a look at the problem because I'm having my doubts too. That seemed a little too easy.
No, that should be right. And also,
that-
will you put that on the test, please?
What's that? Yeah, I was going to say, no, that it is right. Yep, I did it right. So
Yeah,
the force,
that is
the force
right.
will be a vector. So you just multiply by the 10,
10, yeah.
and so you get, all right, negative 250. I guess that'll be newtons, right? That's a 0. Seems like an
And we
awful lot.
don't have to square that 250 or anything. We just start.
It's good to go. Yeah, I think
It
because
goes up.
it's just mass times acceleration. So,
So it's m times vector a, vector
yeah, so mass times a at 0, and yep, you just get a boring 3-part vector like that. So my instincts were right, but I was having this feeling like that shouldn't be that easy. I mean, we're trying to make this hard on you guys. That's the whole point of this, right?
No, we're good.
All right. All right. Anyway, if there had been like obviously a different, like say pi over 6 seconds, yeah, just pop the numbers. You'll get non-zero values, and then I guess just leave it alone. Take those values and just multiply them by whatever the mass was.
Right.
All right.
On the slides for 10.9, there's example 4 is an object of mass m moves in a circular path. And
Yeah.
so I kind of think got a little bit tripped up on that. I didn't need to worry about any of that. I could just work through this.
Yeah. Hey, one thing I want to note is ignore it. It turns out that this third component in this problem is essentially irrelevant because we were doing this at 0. But one of the cool things, if you don't have a third element, if you're just moving in a circle, take a look at the acceleration vector relative to the original displacement vector, and you'll notice that you're back into sine 2t cosine 5t but with negatives in front. Now there's going to be some coefficients, of course, but this goes to show that the acceleration vector points directly inward, back to the origin relative to the displacement vector, and that's classical centripetal force motion. So when you're twirling, I guess when you're twirling an object in a circular fashion, the acceleration comes right back at you. Comes right back at you to the origin relative to the displacement.
Can I have you do number 10? For some reason, I got a very big number and I don't know why.
Yeah, actually, you will get a very big number because e to the 10 is huge. Let me share the question here.
Okay.
Um, number 10 is arc length. Now, this is a good, I'm going to discuss this with you guys. This came up in ed discussions. Um, sorry about that. There it is, number 10 right there. Find the arc length of this curve. It's 10 rad 2t, e to the 10t, and e to the negative 10t from 0 to 1. Okay. Um, the arc length is given by the integral of the magnitude of r prime, which this is just purely formulaic. Um, I'll just do it right here. R prime is 10 rad 2, 10 e to the 10t, negative 10 e to the negative 10t. And when you take the magnitude of all that, you get this monstrosity. You get, well, this squares, this will be 100, this will be 200, this will be, this whole thing squared, the 10 e to the 10t squared would be 100 e to the 20t, and this will be 100 e to the negative 20t dt. That's just me just performing the raw calculations. Any questions up to that point? Okay. And now here's, save yourself the grief. Don't even try to work this out. Just do it on Desmos. So you guys have access to Desmos. If you don't mind, I'll bring up Desmos and I'll share it. Um, I'm going to share Desmos right now. There you go. So you do int, lower bound 0, upper bound 1, square root. What we got going on here? We got 200 plus 100 e to the 20t plus another 100. Remember this minus, the front minus goes away. This inner one does not. And do you guys see that? I get 22,000.
You forgot the second E.
I did, didn't I? That's why it's not correct.
Can I also pause you right there?
Yeah,
So, and this is one of the example videos. If you look under the lesson that it's under, if you factor out a 100, then that's a 100 is a square root. And two plus e to the 20th t plus e to the negative 20th t, that's a perfect square.
it is. But I guess my point is I still get the same answer. Let me just retype this because I want to make sure I didn't mess Desmos up.
No, the last one was correct because when you have e to the negative 10, it's so small it doesn't matter.
That's right. Yeah. So he gets this crazy number, 22,026.46 blah, blah, blah units. Yeah, this is a huge, this curve, I mean, e to the 10 is a gigantic number. And as far as, I'm not even worried about the graph. I'm just working out the calculation. Did you guys see how I got the integral up? I just typed in int, and then that automatically gives you an integral. Then you can fill in the bounds. I'm going to stop the share. All right, so I want to make a discussion point here. In regards to working this out, it's time consuming to work these out by hand when, for one thing, it will accept a decimal answer. So I'm not really concerned about if you can work out the integral of the antiderivative, because ultimately that's not the important thing. The important thing is setting it up correctly. Okay? Because this thing here is actually important for later on.
How many decimal places of precision do we need for the answer?
Well, I don't know. Give me 4.
Okay.
But
Because
the
in the
point of,
homework, I will often copy and paste from Desmos, but I realize that's not allowed under on a lock.
right, physically type it in.
Okay.
I don't care. I really don't care. It's gonna take you 10 minutes to work out the antiderivative, and you're being timed anyway, so it's a time waster. In Calc 2, this might have been a question we would have asked you to work out as an antiderivative. But in Calc 3, it's not really important to work this out. But what's more important is the relationship that develops between the two types of segmentation. This is going to be relevant for later on. Now, of course, in this class, later on is like 3 weeks. But when we get to the chapter on line integrals, surface integrals, flow integrals, things like that, there's two types of segmentation that occurs. There's the DT segmentation, which is the one you normally do when you parameterize a curve. And there's the DS segmentation. What the DS segmentation is doing is it's actually forcing a consistent segmentation of the curve. Unfortunately, the DT segmentation doesn't do that. But on the other hand, the DT segmentation is the easy one. So us human beings will want to do the DT type segmentation because it's easy. But for the math, we need the DS. So this is the little formula that relates the two. So interestingly enough, later on, you won't be asked to do arc length, but you will be asked to work out integrals where this thing shows up, and this is how you undo it. So it'll be an important thing for later on. You know, I don't really care how long the curve is, but I do care that you're able to set this up correctly.
So if we do work out the integral and we get negative or e to the negative or e to the 10 minus e to the negative 10, that's still an acceptable answer.
Well, you're going to be typing in a numerical value. It's not asking for the antiderivative.
Right,
So,
but so when you do the or when you evaluate it, the answer comes out to e to the 10 minus e to the negative 10.
as long as it's correct. Yeah, I
Okay.
don't know what that is offhand. I'm going to type it in. So e to the 10. Yeah, that's what it is. Yeah. As long as it's correct, it'll be accepted.
Awesome, thank you.
Yeah. All right. So again, this is one where you can kind of buy a little time. You make sure that you get this part set up right. And then let the Desmos give you the number. All right.
On the normal vector. Sorry, first thing we did was we found the normal vector of A, B, and C from the plane we were given. And then we found a vector U between a point P that we were given and some point Q that we chose by setting two of the variables to 0.
Yeah.
And in this case, using X and Z was the best choice because it left us with just whole numbers.
Yep.
Then we projected U onto the normal, and that gave us our distance.
Yes. Perfect. Yeah. You're kind of building this brick by brick. And I believe I have an example in my written notes that does this, including like a 6-panel. If I can find it, if you give me a moment here, go to my web page.
Would have been in 10.3 or 10.2. 10.
That would probably be like 10.5.
Oh, okay.
My web page is not loading. Oh, that's lovely. Oh, there it goes. So I scrolled down. I'm going to share the screen. Let me go back just one tiny bit. I'm right here. So this is my web page. I'm right here. Planes and R3 and distances. And then right here, yeah, I have a kind of like a how-to. So you have a plane. I call it Q. You have a point not on the plane. You can infer the normal to the plane by the coefficients of the plane. Create any vector from a point in the plane to Q, put their feet together, do a projection, find the magnitude.
Page, that's 10.5 type examples.
Yeah, if I stop, let me go back a screen. If I do this, so I have, these are my, these are my PowerPoints I use normally in my lecture. A lot of what you see in here are actually taken from here. Not everything from these guys is put into here because otherwise it would be too long. But yeah, so it was this link right here. Oops, right, that one. Planes in R3 and distances. Now I have some practice problems here too that you can try. This dates from like, probably 20 years ago, and I've been adding to it over the years, but these are more practice problems that you can always play with if you want to get some extra web practice. And then I've got answers here, and I can guarantee you every answer here is correct because I've had these up probably since the mid 2000s and plenty of time for people to point out any mistakes. So I'm confident that the answers in this test one practice problems are accurate. As far as summarizing this, I can't do it in just a few minutes. I would suggest make sure that you understand how to build a line and how to build a plane, using the whatever you're given. A line needs a known point and a direction vector. A plane needs a known point, so a point in the plane, and a normal vector. So interestingly enough, the normal vector does not lie in the plane. It lies orthogonal to it.
I have a quick question
Uh-huh.
about the distance from the point to a plane. I have a different formula for it, and I just wanted to know if it was like a proper formula or counterproductive to be using. I have the distance simplified as being the absolute value of A x sub 1 plus B y sub 1 plus C z sub 1 minus D all over the square root of A squared plus B squared
It's
plus C
probably
squared,
going to be the
which is
same thing.
magnitude. I think
Yeah.
it simplifies to the same thing. But that's how I have my projection, like the formula for that. That's how I have it written down. Is that,
Yeah, I
and
could do
in
this
that case,
generically. I could actually just do this generically, and it'd probably be the same thing. It sounds like it's the same thing.
but in that case, I'm just subbing in the point as my X, Y, and Z into the equation for the plane, and then just taking that, making it equal to 0 so that D is equal to -4. And then
Right, right.
so that, but is that counterproductive to do it that way?
If it works for you and you get it right, no, it's not. And it's just,
Okay.
it sounds to me like it's the same thing because
Okay.
it should be the same thing. I mean, you can kind of see the elements going on here. If you stand back, let's say you didn't do anything in the middle here and you just saw this answer. The 11 came from doing a dot product with some vector, that we chose. And again, if I do this generically, well, first of all, the rad 35 and the 35 would be the normal. This rad 35 is mag n, and the 35 is mag n squared. And so, yeah, it is hard. I think what you're looking at is just simply a generalization of the projection formula.
Okay, great. Thank you.
If you're getting them right, I mean, I've seen the formulas, and I certainly I think they're correct. It sounds to me like what you would do in a case like that, the way to prove it would just use generic points. Like call this point P, call it, X naught, Y naught, Z naught, and call the plane AX plus BY plus CZ equals D, and then just work it out using letters, but doing the
Right.
exact same steps. And I'll bet you get something that looks like what you just described.
Yeah, basically. Okay.
In fact, I challenge you to do it on your own because I think it's all algebra. That's all it is. At that point, you're just messing around with a lot of algebra, but it should work.
Okay.
Yep. All right. We have maybe one more quickie question. All right. I'll have this up probably within about a half hour. And so the test starts at 4 p.m. Mountain Standard Time. That's in Arizona. And it ends tomorrow night at midnight Mountain Standard. I know that Arizona's can get a little confusing because we don't change clocks when everybody else does. But right now, I think the whole country's on standard. And so for reference, we are 1 hour ahead of the West Coast and 2 hours behind the East Coast. So just, if you're not sure, just Google it and just to make sure that wherever you are, it matches up our times. And somebody's
I got a
entering.
couple questions about the exam.
Yeah.
So, and this is the first math class I've taken at ASU, so it might be, I just want to know what to expect. So, in the syllabus, I think it said you get two chances not
Uh-huh.
to take the test twice, but a second time. When after you're finished the test and you get the score, are you still in honor lock and then you roll straight into re-looking at that, or how does
No,
that work
okay. It's
exactly?
the nomenclature is a little. You've taken the test once, but you
Uh,
get two. You take the test once like normal, and then you submit it, and it should show back the ones you got wrong. With whatever time you have remaining, you can go back and fix those ones you got wrong, and then that's your second chance, so to speak. And then you submit again, and then you're done.
okay.
So it's like you get like kind of like a free grading the first time through. It'll say, okay, you missed 5, 7, and 12. Redo those, and then you can fix those with whatever time you have.
Okay, yeah, I just want to make sure if it was like the everything stopped recording and then you have to get in back into it and then start
No, no,
whatever
it's all
session.
self-contained.
Okay.
It'll be pretty straightforward once you do it once. You'll stay in honor lock, and it'll still be active. You'll see the ones that you got wrong, and then you just just try to fix them. Check for syntax. A lot of times mistakes are because you just simply mistyped a statement, um, things like that.
If you did
Yeah,
the practice exam, it's almost the exact same thing as like after you hit submit and it literally just pops up red on the right side, those little
Yeah,
circles, they'll pop up red and then you can go back and redo them.
Yeah.
So
yeah.
just
And
it's just like that.
and as a general piece of advice, I would like to add that you can define variables in the Desmos calculator, and that does reduce data entry errors in my experience.
Yeah. I'm going to give you all four Desmoses. So you're going to get scientific, calculator, matrix, and 3D. Don't know if you need them all, but you'll have them. All right, I'm going to go ahead and power down, and I'll have this up on my. I'll send out a link when it's ready. So it's going to take about a half hour. And I'll be monitoring. So when it starts today, I'll be basically sitting by my computer because invariably there's always something that I didn't do, so I have to fix it. But good luck to everybody, and I should have scores for you by Sunday. All right, so 3, 2,
Bye.
1.
Thank you.
Bye bye.